rational functions. In the past, we've solved rational functions. However, this time we're going to talk about their graphs. A rational function is simply a polynomial divided by a polynomial where we have to ensure that the denominator polynomial, where it's not equal to 0. Because as we know, if we solve for the denominator and it becomes 0, we cannot divide by 0, so it's undefined. So we have to identify those places within the rational function. So if we were to consider the function 1 over x minus 3, let's find the domain of the graph. So we know that the domain is all the values of x. However, we have to exclude those values where the denominator would be 0. So when I set x minus 3 equal to 0 and solve, we need to avoid where x is 3. So x such that x cannot be 3, or negative infinity to 3, you skip over 3 back to infinity. And when I graph this, we see that we have a vertical asymptote here. And that's why we're skipping that value. So let's determine of each of the functions below what their domains should be. Right off the bat, when I look at 1 over x, I know that x simply can't be 0 by itself. It can be any other value, or negative infinity to 0 union 0 to infinity. The same is true for 1 over x squared. The only value would be 0. So x such that x cannot be 0, or negative infinity to 0 union 0 to infinity. When I have x minus 3 over x squared plus x minus 2, we need to factor the denominator in order to determine the values. Here we're plural values. So what multiplies to negative 2 but yet adds to positive 1? Here we found positive 2 and negative 1. When I set each one equal to 0, x cannot be negative 2 and x cannot be 1. Or written in interval notation, negative infinity to negative 2, skip over from negative 2 to 1, skip over, and from 1 to infinity. 2x plus 5 over 2x minus 6, I'm going to factor the denominator. They both have a 2 in common, so I'm going to factor out the GCF of 2. When I solve x minus 3 for 0, x cannot be 3. Or from negative infinity to 3 union 3 to infinity. Similarly, I've got a quadratic over a quadratic. I just need to factor the denominator. So what multiplies to negative 2 but yet adds to negative 1? Positive 1 and negative 2 work. When I set each one equal to 0, x cannot be negative 1 and x cannot be 2. And finally, x plus 1 in the denominator, I know that x cannot be negative 1. So written in interval notation, negative infinity to negative 1, union negative 1 to infinity. So let's determine those vertical asymptotes. The vertical asymptotes of a rational function where there's polynomials and they have no factors in common outside of constants, it comes into play with the 0 of the denominators. Anywhere where there's a 0 in the denominator, once we simplify, will become our vertical asymptotes. So let's look at part A. I have 2x minus 11 over x squared plus 2x minus 8. We're going to factor that denominator so it multiplies to negative 8 but yet adds to 2. 4 times negative 2 would work. So our factored form would be x plus 4, x minus 2. I noticed that in my numerator and denominator, they have no other common factors that we can simplify. So we want to look at the zeros of our denominator. Our zeros are negative 4 and positive 2. So we're going to have two vertical asymptotes, one at x equals negative 4 and one at x equals 2. On the right here, I've got the graph from Desmos, and we can see when I put in our dashed line for our vertical asymptotes, that there is one at -4 and then another one at +2. Our graph gets super close to those asymptotes but never actually crosses those asymptotes. Okay. Let's look at, we need to determine the domain. The domain then, just for practice, goes from -infinity to -4, union -4 to +2, union 2 to infinity. Let's look at x squared minus 4x over x cubed minus x. Let's first factor the numerator and the denominator because I see that I can factor x squared minus 4x. They both have an x in common. When I factor out x, I have x minus 4. When I look at my denominator, I also see that they have an x in common. So when I factor out x, I'm left with x squared minus 1, which we can factor using the difference of perfect squares, providing us with x plus 1, x minus 1, and then x minus 4 still in the numerator. Notice that I can simplify because we have a common factor in the numerator and in the denominator. Let's look at the zeros of the numerator. The zeros of the numerator are 0 and 4, and the zeros of the denominator would have been 0, -1, and 1. But because we simplified out the 0 of our x value, we only need to look at the vertical asymptotes of -1 and 1. Again, I have the graph on the right-hand side here. Here's -1, and here's x is +1. Our next example, I have x minus 2 over x cubed minus 5x. Our numerator is already factored and simplified, but I noticed that in our denominator, we can simplify by dividing out an x, the greatest common factor. When I do that, I have x times x minus 5. Notice that they have no common factors in the numerator and denominator, so we have to look at our denominator. The zeros of the denominator are when x is 0, so when we set x equal to 0, when we set x equal to 0, and when we set x squared minus 5 equal to 0. So x is already set equal to 0. I add 5 and take the square root of 5, so I've got plus or minus the square root of 5. Right, so here would be 0 as an asymptote. And here, kind of in the middle, since it's not a whole number, here's negative square root 5 and positive square root 5. So these are all vertical asymptotes that we've been finding, and note that our graph should never cross that vertical asymptote. Let's talk about finding horizontal asymptotes. I've got two polynomials, -7x to the 4th minus 10x squared plus 1 over 11x to the 4th plus x minus 2. Notice that the numerator and denominator are the same degree. They have the same degree of 4. The horizontal asymptote is given when we take y is equal to a over b. This is our horizontal asymptote, where a and b are the leading coefficients of the numerator and denominator respectively. So I notice that they have the same degree of 4. I know that I'm going to have a horizontal asymptote when I take the coefficients of, just as we see at -7 over 11, or if we put it into decimal version, -0.63 repeated. So we've created a horizontal asymptote. because their degrees were the same. Find the horizontal asymptote of 2x plus 3 over x cubed minus 2x plus 4. Notice that our top polynomial has a degree of 1 and the bottom polynomial has a degree of 3. So if we think about the direction in which our graph is going, as our x values are increasing, a degree of 3 polynomial will also increase, however much faster than that of a degree 1 polynomial. Just thinking about the graph itself. So as x is going to infinity, the polynomials, when we divide them, will be getting closer to 0. And if x is getting more negative, the polynomials, when we divide them, are also going to get closer to 0. So logically thinking through the values of our graph, we can say that the horizontal asymptote is 0. Oops. This will happen anytime the degree of the numerator is less than the degree of the denominator. So anytime the numerator is less than the degree of the denominator. So here are the degree of the numerator was 1, and 1 was less than the degree of the denominator with 3. Anytime that happens, we can automatically assume that there is a horizontal asymptote at 0. So let's go to some formal definitions. When the numerator and denominator of a rational function have the same degree, when they are the same degree, the horizontal asymptote is y is equal to the coefficients a over b. When the degree of the numerator of a rational function is less than the degree of the denominator, we have a horizontal asymptote automatically at y is 0. However, when the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote like the first couple of examples that we had. Graph the function g of x is equal to 2x plus 1 over x squared. Include and label all of the asymptotes. We have to look at the denominator first to determine the vertical asymptotes. The only place with which x squared would be 0 is when x itself is 0. So x is 0 is a vertical asymptote. When I look at determining my horizontal asymptotes, I look and I see that the exponents are the exact same. So because the exponents are the exact same, I know then that my horizontal asymptote will be the coefficients 2 over 1, or y is equal to 2. So we have a horizontal asymptote at y equals 2. We can plot some points, and I just list some points here, but on the right you can see that this is a Desmos graph. I definitely encourage you to use Desmos to help you verify that what you're finding algebraically with respect to vertical and horizontal asymptotes actually match what we see on the graph itself. Sometimes we may have a graph that is neither horizontal nor vertical as an asymptote. We call these slant asymptotes or oblique asymptotes. Let's look at 2x squared minus 3x minus 1. Let's look at the denominator to determine any vertical asymptotes first. We have a vertical asymptote when our denominator is 0. When I set x minus 2 equal to 0, we have a vertical asymptote at x equals 2. So I have the graph listed here below. So here's x equals 2. There are no horizontal asymptotes because when I look at the degree of my numerator over the degree of my denominator, it's bigger on top. But in this particular case, and I want you to star this, when the degree of the numerator is 1 more than the degree of the denominator, so 2 is 1 more than 1, we need to actually divide and find the equivalent expression because this is going to provide us with a slant. When I take 2x squared minus 3x minus 1 and I divide it by x minus 2, you can use synthetic division that we learned about, or you can use long division to divide out. But when we divide out, I end up with 2x plus 1 with a remainder of 1. But I'm only curious about this 2x plus 1 piece here. I'm only curious about that part. That 2x plus 1 is going to be our oblique asymptote. And notice it's written as a linear equation. So I can start at positive 1, rise 2 over 1, rise 2 over 1. And notice you'll see that our graph is using this as a oblique asymptote. (2x plus 3 over 3x squared plus 7x minus 6). Let's first find the zeros of the denominator so we can identify any vertical asymptotes. I need to factor that 3x squared plus 7x minus 6 in order to determine where it's set, where it's equal to 0. I have a larger number in front of x squared, so I need to find what is 3 times negative 6, which is negative 18. Multiply to negative 18, but add to the middle number of 7. This provides us with 9 times negative 2, which adds to 7. I'm going to rewrite this as 3x squared plus 9x minus 2x minus 6. Kind of grouping two that have common factors together. The ones on the left are divisible by 3x. So when I divide by 3x, I'll have x plus 3. When I divide the right side by negative 2, I have x plus 3. They have a common binomial, which I'll factor out as x plus 3, and then I'm left with 3x minus 2. I set them both equal to 0. 3x minus 2 is 0. When I simplify, we have x is equal to 2/3. And when I simplify x plus 3 equals to 0, I end up with x is equal to 3. So we have 2 vertical asymptotes, one at 2/3, at x is 2/3, and then one we see here at negative 3. The degree of the numerator is less than the degree of the denominator. So the degree of the numerator is 1, and that is less than the degree of the denominator of 2. So we automatically know that we're going to have a horizontal asymptote at 0. The 0 of the numerator tells us the x-intercept. So any 0 of the numerator tells us the x-intercepts. When I have 2x plus 3 equal to 0, when I take my numerator and set it equal to 0 and solve, we'll have negative 3/2. This tells us that x is equal to negative 3/2. So it tells us the x-intercept is right here. This will help if you're graphing by hand. We certainly are using Desmos to help verify some pieces, but putting some other pieces together is helpful as well. If it has a y-intercept, we can find it. We know we can find the y-intercept by replacing our x value with 0 and solving. So when I plug 0 in for my x my x values, these disappear. I'm left with 3 over -6 or -1/2. And now I can see my x-intercept is here. But again, use decimals to help us graph these. X squared minus 1 over x squared plus x minus 6. Let's look at the denominator and determine where we'll have vertical asymptotes by setting it equal to 0 and factoring. When I factor, I'll have multiplies to -6 but adds to 1. Looks like +3 and -2 work. When I factor and set equal to 0, I'll have 2 vertical asymptotes at x is equal to -3 and x is equal to 2. We can see that looking at the visual graph itself that is the truth. Let's look at vertical asymptotes. The degree of the numerator is the same as the degree of the denominator. So y equals 1 is also because of the same degree, we take the coefficients of 1 over 1, which is 1. So we also have a horizontal at y equals 1. We can determine the zeros of the numerator by factoring the numerator and solving. So when I factor using the difference of perfect squares, I have x plus 1 and x minus 1. Solving tells me that my x values are going to equal -1 and +1. We can find the y-intercept by substituting 0 in and solving. When I solve, I have 0, 1/6. And that helps build our graph for us, otherwise using decimals to help verify. We have g of x is equal to x minus 2 over x squared minus x minus 2. Let's first look at our denominator and factor the denominator. So what multiplies to -2? What multiplies to -2 but yet adds to -1? Looks like -2 times 1, which gives me x minus 2x plus 1. Notice this is the first time that we're able to simplify. We have a common factor in our numerator and in our denominator. So the denominator is equal before we simplified to 2 and -1. However, we got rid of x minus 2, so we got rid of x equals 2. So when I'm thinking of, our domain has to be still -1 and +2, but the only one, since we canceled out, the only vertical asymptote will be at -1. But we also know that x cannot be 2. And in this case, if you were to hover your mouse over this graph, there's going to be a hole here. So we need to put a hole here because x cannot be 2. So the simplification tells us where our vertical asymptotes are going to be. But even though we're canceling it out, we still have to consider that x can't be that value before we simplify. 2 is also a 0 of the numerator, so the only vertical asymptote that we talked about is x is -1. I also see that the degree of the numerator is less than the degree of the denominator. So we also have a horizontal asymptote as 0. When I simplified, I would end up with 1 over x plus 1 with the understanding that x cannot be 2. So it's showing the graph of 1 over x plus 1 with our hole at x equals 2. Here we have negative 2x squared minus x plus 15 over x squared minus x minus 12. Let's factor the numerator and denominator. When I do that, I see that they have a common factor of x plus 3. So I know that x cannot be negative 3 and x cannot be positive 4. So thinking about our domain, we know that's the truth. The only asymptote that we'll have then is at x equals 4. And that at x is equal to negative 3, since that's the place with which we canceled out. X equals negative 3, there's going to be a hole here because x cannot equal negative 3. When I'm looking at the degrees, I see that they have the same degree. So our horizontal asymptote will be our coefficients, negative 2 over 1 or negative 2. So I know that I'm going to have a horizontal asymptote here. The zeros of the numerator, when I set each piece of negative 2x plus 5 equal to 0, and I set x plus 3 equal to 0 and solve, my zeros for my x-intercepts are going to be 5/2. So here's my 0. And negative 3, but we've already decided that negative 3 is not in the domain, so we can ignore that one. We can find the y-intercept by substituting x for 0, and when we do, we have 0, negative 5/4. So here's our y-intercept. And we can find at what particular point that hole is at. Once we simplify to, once we factored and we simplify, we have the function negative 2x plus 5 over x minus 3. When we substitute in f of negative 3, we have negative 2 times negative 3 plus 5 over negative 3 minus 4, which turns into 6 plus 5 over negative 7. Or the exact point that this hole is at negative 3, negative 11/7. If you're looking for a specific value where that hole is at. And one more application. A person's temperature T in degrees Fahrenheit during an illness is given by this function. 4t over t squared plus 1 plus 98.6, where t is given in hours since the onset of the illness. Let's find their temperature at 0, 1, 2, 5, 12, and 24 hours since the onset of an illness. When I substitute these values in, we end up with 98.6, 100.6, 100.2. We now start falling again, and then we're down to 98.766 after 24 hours of this particular instance. Let's find the horizontal asymptote of the graph. In order to do that, I need to create one single graph or one single polynomial right now, or excuse me, one single rational expression. Right now, there are two individual ones that we're looking at. So in order to do that, I'm going to have to multiply the numerator by t squared plus 1 over the denominator of t squared plus 1 for that common denominator with the 98.6. This gives us 4t over t squared plus 1 plus, distributing here, I have 98.6 t squared plus 98.6 all over t squared plus 1. Since they now have a common denominator, I can add my numerator together which is simply the 4t plus 98.6 t squared plus 98.6 all over t squared plus 1. Now I can rewrite this so it's in descending order. Since I'm looking for a horizontal asymptote, I'm looking at the degrees of them. They have the same degree, so I can look at my coefficients of 98.6 over 1, so 98.6. So as our temperature is approaching 98.6, our time is approaching infinity. This tells me that as time is going on, a person's temperature will return to normal. So as time moves to infinity, our temperature, regardless of the illness that's happening, we will continue to return back to our normal temperature of 98.6. And a graph would verify that as well. And this concludes our lesson on irrational functions and their different properties.